Hello, I'm Paul Gluck, General Manager of TUTV, Temple University Television, and the Cal and Lucille Rudman Media Production Center here on Temple's North Philadelphia main campus, and we welcome you to our first episode of TUTV's Future Focus, where we meet the Temple alumni who are making unique and innovative contributions to science and technology. We begin this series with our eyes on the skies. It's hard to imagine how long human beings have been looking to the stars in search of elusive answers about the mysteries of space, time, matter, and our own origins. But for those who are fortunate enough to study with Temple professor and Temple alum John Helferty, using NASA rockets to unlock some of the secrets of the universe is just a part of the syllabus. Please join me in welcoming a respected member of faculty and the director of the Student Space Exploration and Environmental Systems Laboratory at Temple's College of Engineering and Three Stooges fan like myself, Professor John Helferty. Welcome.
Paul, thank you
Thanks
very much.
for joining
Pleasure
us.
to be here.
Well, it's our pleasure. You do something with students that's most unique. I mean, we talk about experiential learning. Some of us can bring students to a TV studio or take them to the zoo. You take their work and launch it into space. Often I've wanted to launch a student into space, but still, you launch their work into space.
Yeah, absolutely, yeah.
So before we get into all of this and all the sort of geometry of how you teach and the benefit for the students and perhaps for science and engineering as well, you are Temple made, as the expression now goes.
Yes, certainly. You cut me, I'll bleed cherry white.
Well, we're not that violent. You're mistaking us with another program on TUTV. We're not Al Sports. Here's the question for you. How'd you wind up here? I mean, because you seem like a relatively bright guy. How'd you wind up in the streets of North Philly?
Right. No, it was, I grew up in Delaware County. I'm homegrown.
Really? Where'd you go to high school?
I went to St. James High School in Chester. I was there from 73 to 77. And I was fortunate enough, I was one of those guys that, what really turned me on to the space stuff was I remember seeing the moon launch and all that, but it wasn't that. It was the actual launch and seeing of the Voyager spacecraft. Oh, the one that would carry its satellite, I guess, right? Well, it was the Voyager spacecraft that the first flybys of the outer planets. There was two of them, Voyager 1 and 2. Matter of fact, that right now I believe Voyager 1 is going through what's called heliopause, which is where the sun no longer has any effect on it.
It's that far from the sun?
It's that far out where it's in. Yeah, now you're on the realm of interstellar space.
So you were a teenager when you saw
I saw that, and I'll never forget. I went to my high school physics teacher at the time, and I said, "Brother Leahy," I said, "I saw this thing on TV." He's there. That's great. And I said, "Look, I'm really interested in this, and that place where they built that machine is where I want to eventually go and work."
And that place was
Jet Propulsion Lab at California Institute of Technology.
Let's back up.
So that was my.
It was your goal.
I needed to get whatever I needed to get as an education, and that was my long-term goal.
Well, let's back up a little bit. So you went to a parochial school.
Yeah.
And I know as we were talking before we started rolling tape, Brother Leahy was an important influence, as many teachers could be.
Absolutely, yeah.
How did he help you resolve one of the great conundrums in science and spirituality?
We had
how do you talk about creation
discussions about that
versus the Big Bang Theory?
I mean, you look at the creationist versus the Darwinian type of thing. It's one of those things. It's just that it's as being a Mariner's brother, faith is what drives him. We had many discussions about it. I'm like, well, don't you realize that this universe is 13 billion years old? He's there, but there was a creator behind this. Somehow, and I go, well, wait a minute, what about the Book of Genesis and things like that? You could get into some philosophical discussions about it, but he was the one. He really molded me, impressed upon me that science was. I had a knack for it and an aptitude for it, and to this day, I still thank that man for that.
Is he still with us?
No, he's no longer with us. So, but it was interesting when I finally made it to California. He came from a large extended family. And I knew, like even during high school, and I kept up with him when I was going to Temple for my undergraduate, that he would make trips out to California. When I eventually made it to the Jet Propulsion Lab, I contacted him and said, "Brother Leahy, are you going to be in California?" He said, "Oh yeah, I'll be out in the summer of 1990. I said, "Good, come on down to Caltech because I'm here." And he couldn't believe it.
Wow. Well, we've always sort of, in my world, we take an answer from Carl Sagan when we try to resolve the spiritual and the secular, which is it just couldn't be a cosmic crapshoot.
Right.
That was one of the great
Right.
quotes from Carl Sagan. But so now
God bless his soul.
You've found your mentor, you found your passion, and eventually you found your way to Pasadena to the Jet Propulsion Laboratory. I guess the question is, where did Temple play? What role did Temple play in that?
Instrumental. It was instrumental, and that's what I have to give Temple the credit that at that time it was an engineering technology school. It wasn't so much of a research focus, but there was a lot of focus on the teaching aspects. And I had some wonderful mentors here. Dr. Brian Butts, who just retired, it was great to be at his, I was an undergraduate under him, under his wing. He was instrumental in helping me get on to graduate school. And it was at Temple's where, that great mentorship is really what helped me to get.
And so you came here, you got your undergrad here, I guess you went to Drexel
afterwards
for your advanced degrees.
Yeah.
How did you wind up making it to California? Not everybody who walks out with a newly minted diploma, meets their aspiration. How did you get to and this was relatively early in your career,
It was very early. I finished my my PhD degree at Drexel was in 1988. At that time, I was doing some work at the Naval Air Development Center up in Warminster. I was doing some teaching here at Temple, and I sent my resume. I looked up the specific people that I wanted to work with at JPL. So that's the thing, you really have to focus. You just don't send out a blind resume, and you guys should all understand
this
that.
Is under the heading of Know Your Audience.
Know your audience, exactly. So I pinpointed very specific people. I was doing what were called control systems. Basically, it's like how you maneuver a spacecraft with thrusters and things like that. So if you're doing pointing and orienting, like if you're doing a planetary flyby and you want to get a look at, let's say, a special feature like the storm cloud on Jupiter or something like that. So what I would do is basically set the spacecraft up to do that. So I specifically targeted the group that was at the Jet Propulsion Lab in guidance and control. And so eventually I sent my resume out. Didn't have email at the time, so it was BE I called before email.
Before email?
Before email. So I targeted
the good old analog days.
Exactly, yeah. Welcome to the digital realm. So I specifically targeted a group there that I knew was doing this work. And lo and behold, I was at the Naval Air Development Center, and they said, why don't you come on out for a job interview?
Were you working at the Naval Air Development
I was at Naval Air. That summer I was working that summer at Naval Air.
And was it still as fully up and running as a research facility at that point?
Oh yeah. Matter of fact, I was working on, at Naval Air, they were actually doing some of the original work on the drones.
Oh really?
The unmanned drones that are making all the headlines over in Afghanistan and all that stuff. And what we were doing at Naval Air was that as a ship, you want to be real stealthy when you're out. Aircraft carriers and stuff, they usually go under, you shut off all electronic communications because electronic communication can get picked up. And they can then triangulate and figure out where you are. Sure. So usually there's a lot of radio silence that's going on. Now, how do I get out and I go out and I find like the Kiev class ships? Well, I can fly up a reconnaissance plane with a guy in it, but that's going to make a radar signature.
Right.
So what we did was we were taking these small little Piper Cub. They're basically 4-foot wingspans. We would fly them off the deck. They would actually have on them a camera and a little GPS transponder, so newer was, and you would fly, they were called ladder waypoints. And what it would do was actually this little drone would just be scanning and looking. And now the ocean's a pretty passive space. When you see something like a ship, an aircraft carrier, you can pick it up pretty easily. So what we would then do is do an ingress towards it, get down low, take a side angle view so then we could classify it, then the plane would come back, and then we'd actually have a picture of it and we would know.
This was obviously pilotless, this was all remote control?
And they were flying, there was no remotes at all.
Wow.
Because you can't have a communication up or down link, because they can pick up the communication link. Too. So these were the first autonomous drones that are out there.
So you were working on what were essentially defense systems.
Oh, defense stuff, yeah.
And then
that's where a lot of engineering gets, and I kind of shake my head at it. I had a student who's just finishing, and he's going to go to a large defense contract. I won't name it.
Sure.
But it's like, I look and
well, there are only 5 of them, so we can guess
right.
that.
Well, it's the largest defense contractor
in the world. It's like television networks. There are only 5 left, so you can name them all.
But and it's just, I look at this guy as brilliant. He does wonderful signal processing stuff using these state-of-the-art processors, and now he's going to go into this vault and just work
and be lost.
And it's great for security and things like that. But I'm like, a student like that, I would love to see be the next Steve Jobs. Go out and design the next consumer electronics.
But you were doing that, and I'm going to guess you were pretty happy just because it sounds like you're excited about the work you were doing.
Yes, because you're working with state-of-the-art technology.
And you were working in sort of a hollowed place, right? I mean, isn't that where the Mercury astronauts trained in the centrifuge? I hope it's still there, the enormous centrifuge.
It's actually called Nastor now. Last semester, my students and I made a trip, and they were inside the centrifuge.
Into the centrifuge.
We have a picture of actually a videotape with their faces all scrunched up, going through about 5 Gs.
And we should probably explain that the centrifuge out there at that facility could accommodate a human being, and the I guess original 7 Mercury astronauts?
Yes, 7. Yeah.
7 Mercury astronauts.
Only 6 flew though.
Right, exactly. Yeah. Who went in the first flights would climb into this thing and be swung around on the end of an arm at 100 miles an hour, 300 miles an hour, 500.
You would literally be going up to like 4 and 5 and 6 Gs in this thing.
4 times, 5 times the force of gravity.
Gravity, yeah.
And it was a spectacular
picture. So if you're 1 pound here and you're at 5 Gs, you're now 5 pounds.
That was always my weight problem.
I
was always
here was
ahead of the
another
gravity.
interesting project up there too. Was speaking of G-forces, you watch these pilots when they're doing a maneuver like trying to get behind another enemy aircraft or something, and they're whipping that stick like this, and literally they have a heads-up display on them that literally weighs like 5 pounds with everything. Now multiply that by 5.
Right.
So now that 5 pounds becomes 25 pounds. They would get whiplash.
Wow.
So
from their own helmet.
From their own helmet, doing such a high G maneuver. So
Phenomenal.
One of the things that we were working on was to actually have, as I'm sitting in the seat, the pilot's sitting like this, holding on to the yoke. We built a robotic arm that basically came up, attached to both sides, sensors inside the helmet. They were called load sensors. So you could feel like your head pushing against the helmet. It would actually lift the helmet up, and he could do his high G maneuvers
to compensate
without feeling the helmet.
Phenomenal.
Yeah.
So now you're doing all that stuff that obviously turned you on, but now you're going to go to Pasadena, and you're going to work on something that is sort of this higher order, perhaps, at least in your mind, right?
Oh, absolutely.
What projects did you work on in Pasadena?
I worked on what we call flexible space structures and satellite guidance and control, and specifically at that time, there was the Galileo mission was going out to Jupiter. All right, and they had what's called on it a Huygens probe. And that was going to be dropped.
That sounds like a Jerry Lewis movie. A Huygens probe? What's a Huygens probe?
It's after the
Huygens probe.
Yes. Huygens, Huygens, yeah.
What's a Huygens probe?
Huygens probe is actually, there's a Titan, which is a moon.
Sure.
Actually, they on the Voyager flybys, they discovered methane, which is actually one of the basic elements of life and things like that. So what they wanted to do, and again, the moon itself is extremely cloud covered. It has this methane kind of shroud around it. But what they wanted to do was get actually a look at what's happening on the surface. So basically, you had the Jupiter spacecraft. One of the things is, how do you stop a spacecraft that's doing 80,000 miles an hour in space? You have to aerobrake it. So literally, what you're doing is, we're coming in, here's the planet, and basically what you're doing is you go inside the atmosphere, and that friction that's generated slows down the spacecraft. So now you get locked into an orbit. So now that you're locked in orbit, then we were just waiting for Titan to come by, and then as soon as they came over to the moon Titan, they dropped this probe that came out and parachuted down onto the surface and was transmitting images up. And there's actually images of pools of methane. It looks like liquid water, but it's actually
liquefied methane.
Liquefied methane on the planet.
So was this the first major project you worked on at the Jet Propulsion Laboratory?
Yeah.
Do you remember the first time you saw images from that probe?
Oh yeah.
What was that like?
It was years later. I had left JPL at that time because it was a really multi-year mission.
Right.
Yeah. This thing, you don't just point it at Jupiter and let it go. You use gravity assist, so it basically passed by the Earth twice before it was on its way and slungshot its way out. So I saw the
German Geslung. But go ahead. So the slingshot took it back out to Jupiter.
The slingshot took it back out to Jupiter, and I didn't see those images until it was years later. But it's one of those things that makes the hair on your neck stand up. It's like, man, you were part of that.
Now, were you teaching during your time?
I was back
there?
here at Temple. Yeah.
Okay, but I mean, during your time at JPL, were you teaching?
No, that was purely
practice.
Jet Propulsion Lab is a laboratory that's run by the California Institute of Technology. Right. And so I was a full-time employee at JPL. But I mean, you could teach over at Caltech, but I didn't choose to.
So what brought you back to Temple?
After my
that
wife,
kind of excitement?
there was a 6.4 earthquake. We were living right at the Rose Bowl.
Okay.
I used to go swimming over Caltech every morning. So I went over at 6 o'clock, came back at 7, and I'm in the shower, blah, blah, blah. And the next thing you know, the shower is rattling. Boom. I'm like, okay, something's not right here. So I get out of the shower in the buff, look down the hallway.
We got that. Go ahead.
And and my wife literally grabs my daughter and heads out the door. Goes out the door. I'll never forget looking up at the townhouse itself. Now, there's 2 layers. We're on the lower layer, and there's another people living above us. I'm watching this wave go down the townhouse.
Wow.
At that point, my wife said, well, I'm still in the buff. I head for the door because I think the roof's going to come down. All the Californian
Still
people
a
are
smart
out there.
move.
Okay, yeah. Here I am, dripping, whatever, and all of a sudden it's like, everybody's like, okay, it's over, it's done with. There was some aftershocks and all that, but my wife said, we're going back east.
Home.
Yeah.
So you began the search, and was Temple the first place you came when you got back from
Temple was the first place I came back. Matter of fact, it was the fellow I mentioned before, Brian Butts. He saw my resume. He contacted the chair of electrical engineering at that time and says, you want this guy back.
So when you came back, was it your intention that you wanted a teaching position?
Absolutely.
Okay.
Yeah.
So you felt like you'd had your time in research and
I
practice, and you
did
wanted
my
to.
thing, and again, it was a family decision. It's one of those, I mean, hey, I had the opportunity. It was my childhood dream. You skied it, hiked it, climbed it. Let's get on with life.
So you get back here, and what are the first programs you work on? I'm going to wonder, did you immediately go talk to NASA about the ability to bring science
Funding
to them?
Well, that was the thing. At that time, NASA has an educational budget, and it's a drop in the bucket compared to what the federal deficit and budget is. But it runs, I think, typically around $25 million. And what they do is that educational outreach it can run through. It actually runs what are called STEM programs: science, technology, engineering, and mathematics. So my goal was what turned me on to science and engineering was space stuff. So I wanted to hopefully turn some students on to space stuff. And that's where basically we started back in I think it was around 92 or 93, started a nice relationship with NASA, got the ball rolling a little bit, and that's where this whole laboratory started to come out.
Well, I want
back,
to take you a little bit afield for a second before we talk about the specifics, because I know there are 3 programs with which you've been involved: the freshman program, and Lunabot, and what is it?
The RockSat.
Go RockSat.
Yeah.
But I have a question, because we are not that far apart in age, though I am older. Growing up as a baby boomer, I can remember a time in the 60s when there was an absolute fascination with what was called the manned, even though it shouldn't have just been men, the manned spaceflight program. Are there still young people out there with the same fascination for space travel that our generation had?
Absolutely. Yeah, but
where have they been hiding? Because they're hidden by all the media kids, it seems to me.
They're at SpaceX.
Are they?
As a matter of fact, 2 of our students had interviewed at SpaceX. They were the ones that just set up the first commercial payload that went up to the space station. Yeah. So
that fervor's still there. We just don't seem to hear much about it.
It's there. It's just, the thing is, it's the way this government is structured. I think that with the wind down of the space shuttle, and I guess the debates over the budgets and things like that, NASA obviously is not doing manned missions now. Right. I mean, that's the thing. They're really letting the commercial side kind of bring that up.
And our former Cold War rivals. I mean, it is not lost on me that
the Soviets,
the way that you take Americans to the International Space Station now is on a Soyuz, is on what is now a Russian vehicle, a Soyuz. Right. So I'm encouraged by the sort of the commercial activity for groups like SpaceX and the Project X things, and even just seeing Felix Baumgartner, go to the
jump
edge of
out on the-
space, and I'm afraid of escalators, and this guy's jumping from the.
You don't want to have vertigo when you're up that
No,
high.
no, I don't think you do.
Because we do fly balloons up to 120,000 feet.
feet.
We have pictures and video, and it's amazing. Yeah.
But would you agree that you don't hear as much about the fervor for space? And for some of us who are thirsty for something like Project Orion to meet fruition, where somebody goes to Mars over a period of a few years, these kids are still out there, and the desire to go to
They're
space is
there,
still
and
there.
it's just, I don't know where you can put your finger on it, but something is lost in America on the science side. It's just not hip.
Anymore.
It really, back in the 60s, you grew up, that was it. It was just, this is cutting edge stuff. Now I think you've lost it in some respects. There isn't that fire in the belly. It isn't, it's let's go out and make the quick buck. Financial field's great to get into, that kind of stuff. But it's...
we did have a period in this country of space fatigue. I do think by the time we saw Alan Shepard play golf on the moon,
ride the little rover,
riding the
little
rover,
buggy,
there was something that said this is commonplace. Sadly, periodically we're shaken to reality when some horrible occurrence, like the fire that killed Gus Grissom in Apollo 1, or the
what got
explosion
us
of a
into
space
space
shuttle.
was the Sputnik.
Right, exactly. It was purely
like,
a military
endeavor.
challenge.
Yeah. Right.
So, but as you find these young people and you give them the opportunity to make their mark in the space program, I understand. So, talk to us about the freshman program, where the hovercraft really is sort of the technical centerpiece.
The idea here is typically when you would go to an engineering program and you're a freshman, you're in with 300 people in an auditorium. A faculty from mechanical engineering would come in and say, this is what mechanical engineering is all about. Somebody from electrical and computer come in, this is what electrical and computer is. And by your fourth lecture, you're like, I'm out of here. No mas. And if you look at it, a lot of students that are in high school, and you think about this in the audience, is I go out to a high school and I'll have a talk with parents or something, and I'll say, did you take English in high school? Obviously, yes. Did you take biology? Yes. Did you take engineering? What? You get that glazed look. Students aren't exposed to engineering at all. Now they're coming to a university, spending a lot of money, and they're getting into a field where they have very little background in. If you really, and that's like, what's going on with your decision to do this? So the idea here is, with this freshman intro class, is to give them really what is engineering, and engineering is design. So one of the key capstone projects we use in this class is a hovercraft, where they have to control it with an iPad. So that's kind of hip. It's, hey, I'm using my iPad to actually control this thing that's going to float and run around on the floor and fly around and whatever. But the idea was to, instead of having them in a lecture hall, teaching by a textbook, give them a project. So the first day of class I come in, I demonstrate a hovercraft, and they all say, whoa, wait a minute. What am I, Dorothy, this isn't Kansas. So it's like, what am I getting myself involved with here? And I kind of talk them through and say, look, you're going to do this. We'll get you through this. So then we break them up into groups of 50, because again, we want a personal relationship with the students. So I will get a group of students, 50 students, and they will do 2 weeks of electrical engineering. The other group of 50 will be getting, let's say, 2 weeks of mechanical, and another group will be getting 2 weeks of civil and environmental and bioengineering, whatever. Then we'll rotate them. So I will then get a fresh group that'll come in and then learn the electrical part. But it's all built around this hovercraft as the capstone project. When they get to the mechanical, they start looking about how to design a skirt, how do you make a bracket. You use AutoCAD, SolidWorks, and things like this to learn the mechanical side. On the civil, they go over and they do structural analysis on this hovercraft. Lift forces, what kind of fan do I need to get this thing to lift off the ground and all that. So it's all integrated around this project. And one of the things, when you go back and look at the feedback forms, a lot of positive things come out of hands-on. Again, tell me, I'll forget. Show me, maybe I'll remember. Let me build it, and I've got it for life. And our retention rates in this class have really been very well. Typically, you would lose 20% of students after their freshman year.
Right.
When I was an undergraduate, basically you didn't even have any engineering until almost your junior year.
Right.
So you have your calculus, your physics, your chemistries, your other courses
Other
you got to take.
sciences and math.
But here I am 2 years and I'm not even. I haven't seen an engineering professor. So the idea here at Temple is we're going to immerse you in a design, and I tell you what, by the time they come out, I know their shoe sizes. I know their mother's maiden name, it seems like, because you have that personal
Yeah, we frown on that in this school.
Right?
But, go ahead.
But that's the idea, is to have a capstone goal at them. The other thing is, what we do is you compete. 40% of your grade is that hovercraft going through. We have a course that's set up. Mm-hmm. And there's prize money. NASA actually funds prize money for this. A couple $1,000s we throw up.
And their goal is what? Because it helps cultivate the next generation of engineers?
Absolutely. Okay. They look for it. This course was actually designed with NASA funds.
So that
I was given what's called, it's basically a grant to develop this course. Now, I let my syllabus out there for everybody. I mean, if you do something for NASA, that becomes open source, which is fine. I mean, that's the way it should be. So the idea was to, now, as you're going through these 12 weeks of learning all the little bits of design, then the last 2 weeks you have to put this together and integrate it into a functional system. So then what we had them do is they have to basically run this hovercraft through like a quasi-maze type of thing. Mm-hmm. But the thing is, that's 40% of your grade. You have to get from point A to point B. And we time you and all kinds of things like that so we can get, so we can judge it. But the long story short is, you've got 150 of your peers that are out there watching your machine go. So it's like being on a basketball court like Temple was with Kansas yesterday. You don't want to miss the foul shot when it comes down to it. You've got 50,000 people watching, who knows how many millions on TV. So you're standing there with your peers. You don't want that thing to putt out on you. You want to make sure it gets through the course. So it's a very good incentive, I find, to do projects where you have to go out there and actively compete. You still have a goal. I mean, as long as you get from A to B, you get your 40% of your grade. But I see that the students, it really ratchets it up a level when you have competitions too.
So now they get to the capstone. This is freshman year. They've done their hovercraft. They've competed. They've run the gauntlet. They've faced off with all the competitors. They know that NASA now may love them. What's the bridge here? Because as I was researching this, some of these kids wind up loading projects into canisters that go on Terrier or Orion missiles that are launched by NASA at Wallops Island, straight up a few 100,000 feet. What project is that now?
That's called the RockSat project, and that's and this is all right. So you get the freshman experience, you learn all this neat stuff. Sure. Now you go off and start learning the real basics of electrical, mechanical, aero engineering, whatever. The idea here is, with this built up depth of knowledge that you had, where can I actually apply this? So my idea was to look at, again, student space exploration, students getting access to space. So a program was run by, and actually the origins of the program are what's called high altitude ballooning. We can get balloons that'll go up to maybe 120, 130,000 feet, and we can sample atmosphere. The balloon eventually pops, parachutes down, we go chase it down, we have a GPS stuff, and that's how it started. So we're actually able to sample like carbon monoxide and things like that that's in the upper atmosphere. So
there's technology that goes aloft with the balloon. You find it when it comes down and you have access to it.
It comes down in high trees.
Right.
One came down on the back of a tractor trailer one
really?
time. We're watching, we're getting the thing coming down and we're watching on our Google map. All of a sudden, it's on the ground, but it's moving. This was out on Route 80 out in Indiana. It's like, no, 70, whatever. But we launched it up in Indiana. It goes maybe 30 miles downrange, and we're watching this thing, and literally we're in the car chasing down this truck, and it's sitting on the back of this thing.
Oh God! So
that was our first experience with getting up to near space, and then this was out of what's called the NASA Space Grant Consortium. There's a consortium out there in every state. Mm-hmm. And what they do is, that's the educational outreach part. That's where that $22 million goes to that, and it's to fund that. So a group of us decided, hey, let's make use of rocket technology. So a colleague of mine at the University of Colorado at Boulder, Chris Kaler, says, hey, maybe we can do something out of Wallops Island. I mean, obviously, we're not going to go down and launch rockets at Kennedy Space Center. Right. Millions of dollars, millions. But actually what we do is at Wallops Island, they use what's called sounding rockets. And sounding rockets are basically scientific instruments that go up into the atmosphere. Sure. They don't go into orbit, but actually they're going to start going. Some of the Orbital Sciences Corporation, sure, they're down there now. That's actually going to be a launch pad to go up into space.
Wow.
We actually just saw one of the rockets last year, a Russian-made rocket too. It's cheap.
It's an ecumenical world. That's why they did it.
Now. But the idea is to give students access to space. So what we've decided is we had Wallops Island build us a payload. And the payload is basically about 5 feet high. We can put in 20 canisters in there. So what we will get is, like we shared a canister with Drexel last year. In previous years, we shared them with Harding University down in Indiana. So we will design a very specific payload that sits.
The payload's a storage compartment, and you put your stuff in it. Okay.
You put it in it, and actually you have ports that are set up so that you can suck the atmosphere in to a port. And that's what we're doing last year we did a biological sample. What we were trying to get was biological samples at different altitudes.
Sure.
And this year we're going to get atmospheric samples at different altitudes. And what you're doing is you're timing these ports. So let's say at 30,000 feet, we'll open up a port, boom, put that in the canister. Open up again a few seconds later when you're maybe at 60,000 feet. Open up the port, boom, so you're getting samples of the trajectory of the rocket and the atmosphere as you're going through, through the trajectory of the rocket.
What's the apex of where you're sending this?
They go up to about 64 miles, 64, 65 miles. And that's pretty consistent, But it's interesting that the Terrier Orion 2s, we don't build them. What they are, they're surplus surface-to-air missiles.
Because Terrier was a war. It was a missile used in the Vietnam War.
Used to shoot down MiGs and whatever. Yes, that's exactly what they are. Yeah. Yeah. So they basically dovetail them, put 2 stages on, and you hit like Mach 6.
Phenomenal.
Hit the afterburners.
Well, in watching a video of one of the launches on your website, I could hear a student say, sort of off mic, I had no idea it was that fast.
Yeah.
When you see this thing just tear straight up, it's such incredible speed. So
and you sit there and think, I've worked a whole year just to see,
right,
and it's gone.
Well, how do they react to that? Because they must be amazed and disappointed in some way. I mean, because it goes by so quickly. It's bittersweet.
It's bittersweet, yeah.
I don't remember it being like that. Wow. Oh my God.
But the thing is, there's a ship that sits off of Cape May Point where we know pretty much the trajectory of it. The ship picks up your payload and brings everything back and all that kind of stuff.
So it lands off of Cape May Point?
Lands off Cape May Point, yeah.
I will never take the Cape May Lewis ferry again. I will not be blown out of the water by your students.
2 years ago, we go to launch, and there was a delay because there was a shark tournament going on for Cape May. The Coast Guard actually had to tell all these shark guys to wait until we did our thing.
Until you hit the mark. Now, you have another project that you do as well, and that's, is that RockSat? No, that's
Lunabots.
Lunabots,
yeah.
Tell us about that.
This, again, is another NASA-driven. It's for STEM, science, technology, engineering, and mathematics. And the idea is, all right, I mean, NASA wants to get students involved in NASA kind of stuff.
Right.
They came up with this thing called Lunabots. And what it is they set up a simulated lunar landscape down at Kennedy Space Center. They set up all kinds of different design requirements. It simulates a moon environment, no air.
Okay.
So on my robots, I can't use ultrasound to do distance measurements. Like we use ultrasounds on robots to do distance measurements and things like that. Can't use it because there's no air. Can't have any air in the tires. Everything
because it would collapse, right?
Collapse, yeah, exactly. What they do is they set up this lunar landscape that has craters, rocks, and what they're interested in is actually having these robots go out and mine this stuff, because actually, if we do go back to the moon, that's going to be like a way station to go on to Mars.
Right.
So what they want to do is mine it and get the hydrogen out of it, possibly H2O, get water out of it and things like that. So then you could use that hydrogen to set off another rocket off to Mars. So what they're interested in is getting these lunar robots to go out and physically do the digging and stuff like that. So, it started out as just basically in the United States, and now it's become so popular, it's opened up to the world. So we're competing with universities from like Columbia, Beijing, Bangladesh.
The BRIC, right? Brazil, Russia,
you got it.
India, China, right?
So, and I think last year, the first year, I think there was maybe 25, and then it went to 36, and now it's well up into 60 or 70. And they've actually capped it because it's just we only have a week to compete, and you get 2 times out there on this playing field. And it's
is this an interior environment? I mean, do they set this up in a vacuum?
It's not in a vacuum. It's actually in
outside.
air. Yeah, because you physically.
But you have to observe the rules of no air for ultrasound.
You have to observe the rules of no air. No, you physically actually, and you have to go into this thing and lift your robot up and put it into this arena, and the arena has webcams on it, and then you're literally in a NASA command center a few hundred yards away. So you can't. The only way you're seeing what your robot's doing is through a link through like a little webcam.
How many students get to participate in this?
Well, last year, I believe it was 61 teams, and typical, I mean, you're talking thousands. I mean, maybe, because our team in Temple had 10. So just take 10 times 61, you know.
Wow.
Yeah, you know.
That's a lot. Or
600, I mean, you can, whatever.
And has NASA found the thing they want in all of these competitions?
Not yet, we're still working on it, yeah.
How does this inform their decisions with something like the Mars Rover? I mean,
well, they look at.
By the way, clearly your students are living this kind of parallel, right? This is a wonderful sort of analog for them to be able to look at the Mars Rover while they're building.
Oh, the curiosity, absolutely, yeah. And it gives the students, like, you know, to do what you're doing on Mars. I mean, it just shows them that, hey, what I'm doing here is a step along the way to doing something like that. And that's quite a lot to be said for that, you know. You know, it's just that fulfillment, the enjoyment of seeing my robot competing out there on a lunar landscape that's similar to what the lunar surface is, and you know, it's just a very, very good feeling.
What's the feedback you get from the students? I mean, I have.
Boy, this is a lot of work.
Really?
Yes, absolutely. The nice thing about a project like this is. It's seniors. We have a senior design, which is our capstone course. Every engineering student has to take it. So I have a group of mechanical and a group of electricals, and we met today. They're working all break, and they have to come up with a design. They have to present their designs to the faculty. But again, this is one of those things where you physically have to have an end product that's going to go down and it's going to compete. So it has to work. Does it have to work the best? We'll see. We'll see what the other teams have. But what's nice also is the freshmen that are in a hovercraft hear about this. Mm-hmm. They start getting involved. So in this student space lab, it isn't just seniors building Lunabots and working on RockSat. I have freshman students that are being part of this team, and they're doing it for no credit. Matter of fact, I have a senior this year that was on the team for the last 3 years, so it goes back to his freshman year. This year he's getting credit for it because it's a senior design. But he volunteered for 3 years, and it was a great experience for him. Put it on a resume. I had just written a letter of recommendation for him to graduate school. The letter was 2 pages long because I know the guy. The guy's done a lot of work, and I did a lot of work for no credit. So it gives students.
It pays to volunteer is the message.
It pays to volunteer. You know what? It should. If this is what you want to do, you don't need to do it just for credit.
Right.
I want to become good at this. So what I like about this is it gives them a real challenge. And this is the real deal, because that rocket's going to fly. That robot's going to go on that lunar landscape. So in the end, you have to produce.
What's the feedback you get from NASA? I mean, clearly they're supporting you.
What else can you do, John?
Well, there you go. That's not bad, though.
Not bad, no.
That beats actually, don't ever call again.
It was interesting. We just held the Pennsylvania Space Grant Consortium meeting, was hosted in Philadelphia last year. They asked me to give a talk on the Lunabots, the Rocksat, and all that stuff. I said, fine. I think it was a 10 o'clock presentation for a half hour. I went up, I had one slide that had the title on it, and then my students spoke the rest. So here's the product of what you're doing. You know, as far as what NASA sees is like, that's great, because they can see where that money went, and they can see that you've kept those students in a STEM-related field. You know, and that's what they want. They're really, that's their focus for NASA education is, once you've got them in, try to keep them in. Challenge them with stuff.
Well, you know, I remember as a young person who was most interested in space, I wanted to be an aeronautical engineer until I discovered that I had no math skills and couldn't draw a straight line with a T-square.
The kiss of death.
No math skills. But I've done okay in TV. We're still paying for the house. But I guess, you know, my memory was of waiting for a human being to stand on the moon, and I saw that. Waiting for the space shuttle to see that, you know, this sort of flying truck system would circle the globe. Waiting to see something that I check in every day on Twitter on the feed from the International Space Station, which just fascinates me that we're up there living and we don't focus on it much. I mean, as someone who's been in news most of his life, the only time you hear a story from the International Space Station is when they have video of a giant hurricane forming.
Or a volcano.
Or a volcano,
like in Iceland, right. Yeah.
Which I think is wonderful, but I know more science is happening up there than somebody's pointing a camera out the window. Your students, what is Mars the goal? What's their aspiration in terms of where man and woman go next in space?
Back to the moon.
They want to go back to the moon.
Back to the moon. That's where you got to start at.
For colonization, or simply as a way station?
Well, you colonize, and
you get a way
that gives you weight. I mean, the two go together, you know. But that's the ticket, is to try to get yourself back to the lunar. I mean, you can see on the other side of the planet, there's a country that's really gearing up towards it. And again, is this going to be our next Sputnik moment, when somebody from China steps foot on the moon?
Well, you know,
then, how did they get there? You know, and we're still puddling around here in in orbit. And
well, how's the argument made? This is an odd thing, I think. Sometimes I think the worst advertisement for sending humans back into space is curiosity. And I'll tell you, the rover on Mars, only because those who oppose the notion of sending humans back in space believe they're getting everything they possibly can get out of, you know, this giant lawnmower that's doing all the science.
Well, it's an SUV.
Okay, so I've simplified because I have no science skills. But I mean, how do we reconcile? Because I can remember in the 60s the argument was there are greater needs on Earth.
Paul, it's a battle. It's always a battle of
man
versus machine. All right, and what are you doing it for? Curiosity's there. Eventually looking for life forms. I mean, that's what it is. It's a science laboratory. So there's that unmanned side of NASA that says, all right, to put a man in space, millions of dollars. Yes, there's a real good argument for stay out of space. It's not natural for us. But again, you've got the unmanned side says, okay, well, we can handle sending them out to Jupiter, you know, out to the outer planets and things like that. Humans aren't ready to go there yet. But eventually you looked at it, we are a society that we're journeymen. I mean, that's how we came up. Magellans that went around the world. I mean,
sure.
You could fall off the edge over there. Well, you can get hurt up in space too, but it still didn't stop people.
No, I mean, we are as sort of, as a species, we're not content.
And I'm not advocating, you know, one over the other. I think there's a complement to each other, and I think there's a purpose for both.
But we do seem, I'll say this, not you, we sort of seem like we need a mission. As a species, you look at the notion of going to Mars, and it's not about writing a new chapter of a science fiction story. It's really about what we can find there that may make life better, the answers we can find that we just can't find here, it seems. You know, is Mars the appropriate next answer after we go to the moon?
It would be the next reasonable one, I would assume. I mean, that would be, you know, but the thing, there's so much technological things you have to worry about in order to just, you know, get. The problem is you're weightless in space. Your body starts to atrophy. I mean, literally, the last guy that came down off the space station, they had to carry him.
Oh.
He couldn't even stand up. They had to carry him because you're losing bone mass and things like that. A lot of big things have to be. I mean, we can talk about Mars. What I like it is it's a goal.
Sure.
It's a challenge. It's, all right, may you get there? I mean, we're goal-driven people. I mean, I sit down with my things to do every day. I got goals every day I got to get done. So it gives me those steps along the way that I know that eventually I achieve it or I fall short and then I figure out why. But at least it's a goal. It's the challenge. And that's, you know, if we get to Mars, fine. Great. I mean, but there's a lot of things that have to happen in between A and B.
And your students are ready to do it, I presume.
Hopefully they're on our way.
Well, first of all, let me apologize because I'm sitting here with an engineering genius and I can't make the clip on my
I
microphone
got him
work.
fooled.
But I want to thank you for joining us. First, I want to thank you for
Paul,
joining us
pleasure.
and for the work you've done for your students
Best
here
of
at
New Year
Temple.
to you. Thank you very
For all of us here at TUTV, thank you for joining us on Future Focus. I'm Paul Gluck. Have a great day.